Hello everyone. In this video tutorial we are going to discuss about the equivalent circulation density and how we can find it. A drilling fluid with the density of 10 ppg and plastic viscosity of 10 centipoise and the yield point of 6 pound per 100 square feet is being circulated in 10,000 feet of drill pipe with the OD of 5 inch and 500 feet of drill collar with the OD of 8 inch. When it says, the question says that we have a plastic viscosity and yield point, that means it's a non-Newtonian fluid. If the minimum transportation velocity is 2 feet per second, calculate the equivalent circulation density or ECD. Use a slot approximation to calculate the equivalent diameter and velocity correlation to find fanning friction factor. The wellbore diameter is 8.5. When it says that the minimum transportation velocity is 2 feet per second, where at which point we have this 2 feet per second. The point that we have this 2 feet per second is the yellow area because it has the maximum area. If we look at the equation for the velocity is equal to flow rate divided by the A. Flow rate is constant inside the drill string and in the annulus part. The thing which is changing is the area. And the minimum velocity is where the area is maximum. The maximum area is annulus opposite of the drill part, the yellow area that is provided in this figure. Now, knowing that, we want to find the ECD, and this equation over here is something that will be provided in the exam condition. You have the equivalent diameter for the slot approximation. We have the apparent viscosity, for the annulus, it has OD and ID, and also the Reynolds number. For the Reynolds number, what is changing is the velocity, the D, which is equivalent diameter, and the mu, which is the apparent viscosity. The F for the velocity correlation provided, and the pressure drop for the turbulent regime also provided. But what is not provided, and you need to remember, is that the ECD equation. The ECD equation is mod weight plus pressure drop in the annulus divided by the 0.052 multiplied by the TVD. So we have mod weight, we have the depths, but we don't know how much is the pressure drop in the annulus. To find that, we have to find the pressure drop opposite drill pipe and the pressure drop opposite the drill collar. To find them, we need to know what type of regime we have. Is that the turbulent regime? Is that a laminar regime? And finding that, need to calculate the Reynolds number. For the Reynolds number, we have rho, we have the velocity for the first part for the drill pipe, but we don't know how much is the equivalent diameter and how much is the apparent viscosity. The equivalent diameter using a slot approximation, the equation is provided over here. The OD is the wellbore diameter, which is 8.5. The ID is 5 inch, which is OD of the drill pipe. If we substitute that, we can find the equivalent diameter, which is 2.85. The apparent viscosity is plastic viscosity, which is 10 plus 5 multiplied by the yield point, which is 6, multiplied by the OD, which is wellbore diameter 8.5, minus the ID, which is for the drill pipe, it is 5, divided by velocity, which in the question mentioned it is 2. If we do the calculation, the apparent viscosity is 62.5 centipoise. Now we have everything to calculate the Reynolds number. Rho is 10, velocity is 2, the equivalent diameter is 2.85 divided by the viscosity, which is apparent viscosity, we found is 62.5 0.5 centipoise. With doing the calculation, we can find the Reynolds number 848, and as it is less than 2000, it's a laminar flow, laminar regime. Then for the laminar regime, to find the pressure drop, because the next step is using the Blas's correlation, it will be easier to find the F for the laminar regime. The F for the laminar regime is 16 divided by Reynolds number. This is for the laminar regime. 16 divided by the Reynolds number, which we found at 848. If we do the calculation, F is 0.1089. The equation that is provided, rho F, is 10 multiplied by the velocity, which is 2. The equivalent diameter is we found it here, 2.85. If we substitute that, the pressure drop will be 0.0103 psi per feet for the pressure drop opposite the drill pipe per feet. Now we want to find the pressure drop opposite the drill collar. First we have to see what regime we have, is that turbulent or laminar. To do that, we need the Reynolds number. For finding the Reynolds number, we need to find the velocity opposite of the drill collar, and also we need the equivalent diameter and apparent viscosity also. So first, as we mentioned, the flow rate is constant, therefore we have the velocity opposite of the drill pipe. We can use the equation over here to find the flow rate. We have the velocity of 2 feet per second. The area is pi divided by 4 multiplied by the 8.5 to the power of 2 minus 5 to the power of 2 for the drill pipe, because we are doing the calculation for the drill pipe to find the flow rate, which is constant. If we do that, the flow rate, it will be 231 GPM or gallon per minute. This flow rate is constant for all the well that we have, for the inside of the drill pipe and drill collar and the annulus part. If we have that, we can find the velocity of the opposite of the drill collar. The flow rate 231, the area pi divided by 4 multiplied by the outer diameter is the diameter of the well bore, 8.5, minus the inner diameter for the drill collar, which is outer diameter of the drill collar, which is 8 inch, and then we need to find the velocity in the unit of feet per second. We need to do all the conversions to have it in the feet per second. Now we have the velocity 11.45 feet per second. We need to find the equivalent diameter. The equivalent diameter is the start approximation. The OD is 8.5, the wellbore diameter, minus the ID is the outer diameter of the wellbore of the drill collar, which is 8. If we do that, the equivalent diameter is 0.4T. And then the plastic viscosity, for the apparent viscosity of the drill collar, the plastic viscosity is 10 plus 5 multiplied by the yield point, which is 6. The OD of the drill pipe of the drill collar, for the drill collar is 8.5, which is wellbore diameter, and the ID is the outer diameter of the drill collar, which is 8, divided by the velocity that we found, it was 11.45. If we do the calculation, the apparent viscosity is 11.31. Now we have everything to calculate the Reynolds number. 928 multiplied by the 10, it was the mud weight, and also we have the V, we found 11.45 feet per second. We found the F, we found the equivalent diameter, which is 0.4, divided by the velocity that we found, 11.31. With doing the calculation, Reynolds number is 3851, which is more than 2000 and is turbulent regime. Now With using the Blastis correlation, because it's a turbulent regime, we have the Reynolds number, we can find the F. After finding F, we can use the turbulent regime finally for the turbulent regime for the annulus opposite of the drill color. Rho F is 10, the velocity is 11.45 for the drill color, and the equivalent diameter for the drill color we found 0.4 multiplied by the F for this part of the drill color, the opposite of the drill color, and the annulus it is 0.01. We do the calculation. 1.27 psi per feet is the pressure drop opposite drill color per feet. Now we can find the pressure drop, absolute pressure drop. For the drill pipe, we found 0.010 psi per feet multiplied by the length of the drill pipe, which is 10,000 feet. For the drill color, it was 1.27 psi per feet multiplied by the length of the drill color, which is 500. Now we have the pressure drop in the annulus, it is 738. Mod weight plus the pressure drop in the annulus, 738. The depth, which is 10,000 for the drill pipe, plus the 500 for the drill color, we can find the equivalent circulation density. That is the ECD that we needed to calculate. But if in the question you are asked to find the bottom hole pressure in the static condition and the bottom hole pressure in the dynamic condition, the bottom hole pressure in the static condition, as we know, it is 0.052 multiplied by the mod weight in the total true vertical depth, which is 10,500. The mod weight it is 10. But when we want to find the pressure, the bottom hole pressure in the dynamic condition, we have equivalent circulation density rather than mod weight, which we found it 11.35. If we do that, in the dynamic condition it's 6,197. For the static condition it's 5,460. If we find the difference between these two, it is 738 almost, which is the pressure drop in the annulus, because the bottom hole dynamic condition, bottom hole pressure in the dynamic condition, is the bottom hole pressure in the static condition plus the pressure drop in the annulus.